Hello, so in this video we are going to start looking at quadratics. Now I actually really like this particular point in the course because the first couple of themes, so algebra and surds and indices, whilst they're really important, they're more about kind of developing skill. So it's a bit like kind of making sure they're nice and sharp and ready to use, and then put them away in our mathematical toolbox, and then we will use them in future themes, right? But this part of the course in particular is kind of the first part of the course where really we get into more the mathematical sort of section. So to that effect, I want to give you a little bit of an overview and sort of give you a little bit of a lead up before we just start with quadratics. So first of all, I want to answer the question, what is mathematics? And maybe you might want to pause the video for maybe 30 seconds or so and think, what do I think mathematics is? But mathematics to me, okay, and I'm by no means an expert when it comes to mathematics. However, I have devoted much of my life for the past sort of 7 years or so to studying mathematics at a university level, and now to teaching mathematics. So I'm going to tell you what mathematics means to me. So mathematics is about patterns, okay? It's about patterns which exist in the world around us. And then we try and understand those patterns by generalizing and using modeling techniques to then be able to transfer that into the abstract world. And effectively, it's about asking the question, why? Why does this make sense? Why does this work? And then it's about asking the question, what if? What if this were the case? Or what if this were the case? And that's how we develop it into the abstract world. So mathematics, in kind of a single sentence, what it means to me, mathematics is the patterns and the connections which exist in the world around us. And the mathematics is kind of the language which helps us to describe the patterns which are happening, okay? So to that effect, I've kind of drawn on the screen here, or taken some pictures of lots of patterns in the everyday world. And we can use mathematics to describe this, okay? So as an example, I've pulled out things like this, which is a honeycomb. Okay, now honeycombs are effectively hexagons, and the reason why they're hexagons is because it means that they can tessellate. It means that they all kind of fit together really, really nicely, so optimal tessellation. And you see hexagons a lot in nature. For example, in the UK, in Northern Ireland, there's something called the Giant's Causeway. This is a geological phenomenon which is caused by cooling volcano magma, and then the way that it cools, the crystal structures which it forms, is these hexagons. And the reason being is because the optimum way of tessellating. Another example, this one here. So I'm not sure. I think this is some kind of creature, but effectively this is a spiral. Okay, and spirals are a really lovely way of describing things in maths. So there's different types of spirals, and it leads us into these things called polar coordinates as well, which we'll look at later. Okay, but even things like this. So this is I think it's an ammonite of sorts. Okay, but certainly, or nautiloid rather. But certainly the way that this forms, the particular kind of spiral pattern which this forms, is something called the golden ratio. Okay, and the golden ratio is actually a number, 1.618, and it describes the optimum ratio, and by the way, this carries on going forever and ever and ever like pi, but this number describes the optimum ratio where beauty occurs, and it's the idea is the optimum packing ratio, and it appears quite a lot in nature, in art, and this has been known about for a long period of time. So sort of if you look at ancient buildings, there will be usually the golden ratio hidden in there somewhere. Okay, but even things like this. Okay, so this is a zebra. Okay, the reason why certain animals have the stripes which they do, it was actually sort of looked at quite a lot by Alan Turing. So Alan Turing is the father of modern day computing, helped to sort of crack the Enigma machine in the Second World War, but he also looked on the side at this idea of Turing stability and Turing instabilities, and it basically helps us to understand the reason why certain animals have the patterns which they do. Okay, so this is all mathematics. Okay, these are all patterns which exist in the world around us, and we use these patterns and we can develop these patterns using the mathematical language. Okay, now one way in which we do that is using this thing called a model. So a model is effectively a simplification. So you look at something in the real world and you try and simplify it down to its core parts and try and understand the thing which makes that situation work. okay? And then once you understand that, you can then be able to apply that to different situations. So let me show you with an example, okay? Let's suppose that we have a guy, okay, a little man, you can see him in his swimming shorts here, okay? And he is diving into a swimming pool filled with custard, okay? So this is my custard down here, right? Now, the thing is, the higher the diver jumps from, the faster the diver hits the custard. Does that make sense? Okay, so if it only jumps from this person only jumps from 1 centimetre above the custard, it's clearly not going to hit the custard with a very high velocity. Okay, whereas if it jumps maybe 50 metres high, then it's going to hit the custard with a much higher velocity because it's fallen for a longer period of time under gravity. Okay, however, and this is the reason why I've chose custard as opposed to water. Custard is what's known as a non-Newtonian fluid. Okay, so Newtonian after Isaac Newton, okay, who is the guy that kind of looked at gravity and things. So custard is non-Newtonian. In other words, if you hit it slowly, it behaves like a liquid. And you can try this. If you've got custard around the house, if you made some up, perhaps you've got it with sort of some nice crumble or something. If you take a bowl of custard, and if you just hit it slowly with your spoon, it will go through and it'll behave like a liquid. And most of the time when we're eating it, we're just hitting it slowly with our spoon and we're eating it nicely. Okay. However, if you take that same spoon and you hit it really, really quickly, okay, then it behaves not as a liquid but as a solid. Okay, so in other words, the custard is dependent on the velocity in which it hits the custard. Okay, so in this case with our diver, if he hits it slowly, in other words, if he only dives from a very, very low height, he'll be fine. It'll behave as a liquid and it'll be good. But if he hits it from a higher height, so he jumps from a higher height, he'll hit it at a much faster velocity, in which case it's more likely to behave as a solid, and therefore the diver's probably not going to come out that well. Okay, so let me model this using some kind of mathematics. So you can see that basically here I've got two variables going on here. Okay, I've got two things that I'm measuring. The first is the height of the diving board, and let's suppose that's in meters. Okay, so how high that diving board is. And then the second variable that we're measuring against is, let's say, how dead that diver is, because we've just established the higher the diver jumps from, the faster it's going to hit that custard, and because custard is non-Newtonian, the faster you hit that custard, the more it behaves like a solid. So let's actually model this using a table. Now I'm going to say that x represents the height of my diving board, because I can't be bothered to type or write the height of the diving board in meters every single time, right? I'm just going to let x represent the height of my diving board. And let's suppose that y is going to represent how dead this diver is. And I don't know, let's just put it in death units, whatever that means, okay? So let's suppose, okay, so let's draw ourselves out a little table. Let's suppose that the diver only jumps from a diving board which is 1 meter high. Okay, so it's 1 meter high. And let's suppose if we measure in these death units, the diver is only going to be like 1 unit dead. So it will be dead, but, you know, not that dead, right? And then if we try a higher and higher diving board, so let's say 2 meters now, okay? Now let's suppose that the dead units of the diver, when they jump from 2 meters high into the custard, will be 4, okay? By the way, I'm just making this up just for the sake of example, okay? Just to show you how modeling could work. And let's now suppose that 3 meters the diver jumps from, and therefore they're going to jump into the custard, and there will be 9 dead units dead, okay? Whatever that means, all right? And then let's suppose we do 4 as well. Okay, so let's suppose they do 4, and let's suppose there's 16 units dead. Let's just try one more. Now let's suppose they jump from 5 meters off the surface of the custard, and they hit the custard, and they're 25 units dead. They're really dead in this case, okay? So what we've basically got going on here is a relationship. Okay, a relationship is between the height which the diving board is and then how dead it is. Let's suppose this is a level of injury or something, okay? So how dead it will be. So 1 is not very dead, 4 is a little bit more dead but still not that dead, whereas 25, when they jump from 5 meters, yeah, they're really dead, all right? Now, the thing is, this is fine. This is one way which we can model a situation as a table, okay? Seeing how one variable changes with respect to another variable. But one way that we can also do this is using a graph, okay? So I've got a graph here, for example, okay? And I'm literally going to draw this table. I'm going to take this table here, and I'm going to represent it as a graph. So there we go, there's a copy of my table there on the screen. Remember, X is the height of that diving board and Y is the level of injury. I'm calling this dead units. How dead is that diver, right? Of course, this is completely fabricated and not meant to make sense in real life, but the point is, I can take this and represent it as a graph. Because a graph simply says, well, okay, as X changes, in this case, the height of my diving board, how does Y change? How does the level of injury of that diver change, okay? So I can actually plot this where the distance across represents the X, represents the height of the diving board, and the distance up and down represents how dead that diver is, the level of their injury, okay? So if you have a look, the first sort of set of points that I've got is 1, 1, okay, 1, 1. So in other words, 1 unit across and 1 unit up. Okay, and then the next one will be 2, 4, so 2 units across and then 4 units up. And the next one will be 3, 9, right? So 3 units across and 9 units up. And then the next one is going to be 4, 16, okay? So 4 units across and 16 units up. And then the last one is going to be 5, 25. In other words, 5 units across and 25 units up. Okay, fantastic. So we get basically a set of points like this. Now what I can do is actually draw a relationship between these points. And the way which I do so is simply by joining those dots together. And you start to get a line that looks something like this. Okay. Now if you have a look at this, I guess this looks something like a bit of a slide. So you can almost imagine that somebody is taking a slide down here, much like the diver jumping to his death in the bath of custard. Okay, but this is my point. So there's different ways in which we can model this situation. Now really, this is where the mathematics comes in. It basically looks at either this table or this graph over here on the right, on the left-hand side, and it asks, how can I model this? How can I mass produce this relationship so that we can use it in other situations as well? So not just custard, we can use it with other fluids and see how the height changes with the level of injury, okay? So the whole idea of modeling is taking a situation that you know about, representing it graphically or using a table, and then trying to mass produce it, trying to then transfer that to other situations as well. So really, what I need to do here is come up with a function. Now a function, so spelled F-U-N-C, T-I-O-N, a function literally says, okay, you give me an input and I will tell you the corresponding output. So in other words, you tell me, in this case, how high your diver is jumping from, and I will tell you the expected level of injury which you get. Now functions work every day, okay? That exact same thought process happens every single day with us. For example, you're looking, if you go outside and you try and cross the road, you're looking, that car is quite far away. Therefore, should I cross the road or not? Okay? The idea of a function linking two things together is happening everywhere in the real world. Also, how cold is it outside? The level of how cold it is will tell you how likely you are to put relevant clothing on. Okay? So the idea of a function is really, really important in every single life. The idea is, you give me an input, you give me something, and I will tell you what you should do in the other end, okay? So X against Y. You give me an input, and I will get an output from that. So numerically then, what this means, if I give you something like 4x plus 6 equals y. So in this case, my input is the x, and my output is the y. So it's a relationship between these two things. So what this literally means is that if I put 3 in this side of my function, okay, this literally says to me, times my input by 4 and add 6, and then I will get my output out the other side. So if I take 3, times it by 4, add 6, that should give me my 18 on this side over here. Okay, so this is the idea of a function. It basically says, just find me a rule that will work for every single input and output that I want. Okay, so if I try a different input, let's suppose in this case I try now 4. Well, 4 times 4 is 16, plus 6 is going to be 22. So in other words, my output is going to be 22. So this idea of a function, it's a way of linking an input to an output. Okay, and this is really useful in the scope of modelling. So before we go any further then, I want to describe to you what a polynomial is, because this is a really important concept, particularly in this section of the course, okay? So polynomial, you can break it into two parts. The first is poly. So poly just means, well, many, okay? And then the nomial bit, well, there's different words which mean nomial in sort of English. If you look at other languages, for example, you might have nombre, which means name, and nom, which means name. Okay, so in this case, a nomial is just a named object. So in this case, my named object is a term. Okay, so the named object is literally just a term. So a polynomial literally means many terms, so something with many terms, okay? Now the reason why I want to look at polynomials is because most functions follow this family of polynomials. So let's actually understand how these are constructed. So we start off with y equals, okay, just like we had before. So y is our output, remember, and we want to do this in terms of x, okay? So I'm just going to write a load of x's down on the screen, okay? So, and it'll carry on forever and ever and ever. So let's just put 3 dots to represent that x's can be loads, carry on like that forever. Then what I'm going to do is just put loads of pluses in between my x's. All right, so I'm just putting loads of pluses in between my x's. So I'm trying to build this polynomial here. So you basically start off with y equals, then load of x's. I'm just going to add all these x's together, okay? And what I can now do is actually start timesing these numbers, these x's, by different numbers. So for example, I could have 3, then I could have 5, then I could have 7, then I could have 6. So basically what I'm doing is adding lots of x's that have been multiplied by some particular number. And just to differentiate this, because of course we saw in algebra that if the x's are all the same term, so if there's loads of x's, you can collect them together to make one term. So just to differentiate these, I'm just going to raise them to different powers. So I'm going to start off with x to the power 0, then I'm going to start off with x to the power 1, then x to the power 2, then x to the power 3, etc, etc, etc. So basically, all a polynomial is, let's come up with some key terms here, okay? So the first is a term. Well, in this case, a term is simply just the bits in between the pluses or the minuses. So each of these things are terms. We've met those before, okay? Now, the numbers which I added in here, so the 3, the 5, the 7, of course, these can be any numbers I like, okay? These are called coefficients, okay? So the coefficients are the numbers which are multiplying the x's, all right? And then finally, the powers are over here. So in a polynomial, the highest power of that polynomial is called either an order or a degree. So let me show you with an example what I mean by that. So the order or the degree is simply just the highest power in a polynomial, okay? So for example, if I give you something like this, let's suppose y equals 5x cubed plus 7x squared plus 6x plus 15. Now you notice that 15 there. You're like, well, hang on a minute, is this a polynomial? Because surely with a polynomial, there has to be x's in every single term. It's just the x's are raised to different powers. Well, are you happy this is still a polynomial? Because the x is just x to the power 0. Because x to the power 0 is just 1. Remember, we looked at that last week with our laws of indices, okay? So this is just a polynomial, okay? Now, what do I mean here? So let's have a look. The terms are the bits in between the pluses. So I have 4 terms in this particular polynomial, okay? And if I have a look, the coefficients would be the 5, the 7, the 6, and the 15, all right? And then the order, or the degree, is just simply the highest power. So in this case, I look at all the terms and I say, what's the highest power of x in this particular polynomial? Well, in this case, the highest power of x is the 3. Okay, so in this case, this would be a polynomial of order 3. So let me write that down. This would be a polynomial of order 3. Okay, reason why it's order 3, you could also say degree 3 as well, doesn't matter. So maybe I put this underneath in degree. So you can say either a polynomial of order 3, or you can say a polynomial of degree 3, that is fine. Reason being is because that is the highest power. So this is going to become really useful when we look at polynomials again in the future. Okay, so polynomials will keep coming up over and over again, hence the reason why I'm introducing it now. Okay, so the really key, 3 key terms there. First one is a term, so the terms are the bits in between the pluses and the minuses. Then you've got the coefficients, which are the bits which are multiplying the powers of x, so the x, so in this case the 3, the 5, the 7, and the 6, or in this case the 5, the 7, the 6, and the 15. Okay, they're the bits which are multiplying the x's. And then the order, or the degree, is the highest power of that polynomial. Okay, so those are the 3 things that I want you to think about. Okay, those are the 3 things that I want you to take away. Okay, so let's actually carry on then and have a look, because I think we've already met, or I think you've already met some polynomials, but you maybe just didn't even know they were called polynomials. Okay, so let me show you with an example. Okay, let's generalize it first of all. Let's suppose we have y equals, let's say, some number. Okay, remember this is still a power of x, but it's just got x to the power of 0 next to it. Okay, plus another number, let's say b, and let's say this is times x. So I'm going to put each term in a different color. All right, and then the next one will be cx squared, let's say. So cx squared, and then the final one, I'll just carry on here to dx cubed, and we're going to carry on like this forever and ever and ever. Now in this case, the a, the b, the c, the d, they're just numbers. Okay, they're just numbers, they're just my coefficients. All right, so let's have a look at the different sort of names which we give different levels of the polynomial. Okay, so if we just have a polynomial with one term, so suppose we have a polynomial like this. So y equals some particular number. For example, we could have y equals 3. Okay, that would still be a polynomial. It's just a polynomial with one term in there. It's just a constant term. Hence, we call this a constant polynomial. Okay, because there's just a number there. All right. If we had a polynomial where it just had two terms, so we had the a, still had the number, the constant term if you like, but we also had the bx. Okay, we also had the bx as well. So for example, we might have y equals 5 plus 3x. Okay, now it doesn't have to be in that order, so we could have 3x plus 5, for example, or negative 2x minus 7. That is also fine. Okay, as long as you've got a number and something with an x in, we call this a linear polynomial. We call this a linear polynomial. Okay, reason being, well, we'll see that in a minute. Okay, we'll see the reason why it's called a linear polynomial in a minute. All right, so let's keep going. Let's suppose we have a polynomial with 3 terms. So we have the a, we have the bx, but we also now have the cx squared. So we have an extra term now. Okay, so for example, we may have y equals 6 plus 2x minus 4x squared. Okay, this we would call a quadratic polynomial. Okay, so basically if you've got the x squared in there, we call this a quadratic. And surprise, surprise, this section is called quadratics, so this is what we're going to focus on in this theme. I will just carry on one extra term because we do also give this a special name as well. So if we have the a, the bx, the cx squared, and that term with the cube in, so the dx cubed. If we had all 4 of those terms, so for example, we may have y equals 6 plus 2x minus 5x plus x cubed, okay, we would call this, and you may already know this, we would call this a cubic. Okay, so that's a really important sort of idea there. Okay, so we basically give names to different levels of polynomials. If the highest power, if the order is 0, in other words, the power of 0 is 0, so remember the first one, still got power of 0, we would call that a constant polynomial. If we had the highest power or the order as 1, just remember there is still a 1 there, we just don't bother to write it, we would call that a linear polynomial. Okay, a linear polynomial. If we have the highest power or the order or degree of the polynomial is 2, we call that a quadratic. And if the highest power or the order of the polynomial is 3, we call that a cubic polynomial. So let's actually see what this looks like. Let's see what this looks like. So what I'm going to do is I'm going to type these different levels of polynomials into my graphing software. So in this case, I've got GeoGebra open. Okay. Now, the really nice thing about GeoGebra is that I don't actually have to draw things by hand. So over here on the left-hand side, it's completely free, by the way. Just go to geogebra.org. Okay. In this case, I've got the classic app open. If you go over here on the left-hand side, you can see that I can type different things over here. So let's actually start by typing in my different levels of polynomials. So let's start off with my constant polynomial. Okay. Let's just say y equals, say, c. Okay, we'll open this up, and what this allows me to do is actually change the value of c. So by default it's plotted y equals 1, and you can see this over here. In fact, I might just change the colour of this. So let's go into colour, let's change this to green to keep it consistent with what we're doing over there. So there you go, okay? And actually I might take the label off. Okay, so this is my polynomial here. So let's see what happens if I change the value of that c, okay? So let's change the value of this. So we got down here. Okay, interesting. Okay, so you can basically see it's always going to be a horizontal line. You can always see it's going to be a horizontal line, okay? All right, now let's see what happens if I add some more sort of terms. Let's say y equals, let's keep that as c, but let's say we add another term in here. So let's say bx, okay? Well, there you go. So now I can change the b as well. In fact, let me change the color. Let's put this to a different color. Let's change it to maybe a purple maybe. So let's find a nice purple. There you go, that will do. Okay, so we've got a nice purple there, okay? So basically if I change the c, you can see that I can basically move the graphs up and down. So the value of the c is basically changing how high or low that graph is. So if I actually hide that for a second, and let's just focus on the y equals c plus bx one. Okay, let's focus on the linear polynomial. Well, you can basically see the reason why it's a linear polynomial is because it's a straight line. And we will look a bit more at straight lines in the next theme. But you basically see if I change the value of b, I'm effectively changing the steepness of that line. I can even make it negative if I want to. Okay, so I can basically change the steepness of that line. Okay, so far we've got a constant polynomial, which is simply just a horizontal line. Okay, then we've just seen a linear polynomial, which is more a line with a slope. Okay, so I can actually change the slope if I want to, and I can also change how high or low that line is. Okay. What's my next polynomial? Well, I guess my next polynomial is y equals c plus bx plus, let's call it ax squared. Okay, let's call it ax squared. Okay, so it's a slightly different shaped polynomial. Let's again change the color, and let's actually change this to maybe an orange maybe. Let's put it as an orange. There you go. Okay, let's turn the label off. Okay, good. So basically what I can do now is changing the c, again, same as before, moves the graph up and down, okay? What happens if I change the b? Well, in this case, if I change the b, I'm effectively, it's doing a bit of a dance, right? Doing a bit of a wobble. There you go, beep, beep. And then basically if I change the a, I'm changing the steepness of that polynomial, okay? So there it's kind of spread out, now it's not. If I change it upside down, ooh, that looks fun. Okay, it looks fun and funky. But basically the a changed the steepness, the b basically changes the kind of wobble, the translation, and then the c is basically moving the graph up and down. Okay, so we've kind of looked at three polynomials. We've got the constant polynomial, which is just a straight line. So this one here, okay, and I can change the value of c. I've got the linear polynomial, which is literally just a straight line. Okay, and I've also got the quadratic polynomial, which looks a bit more like this. Now, quadratic polynomial, this is a really important graph. This kind of U-shaped graph, we give a special name. We call it a parabola. So a parabola is basically this U-shaped graph that is a result of a quadratic polynomial. Now, we did also look at one other polynomial, which was our cubic polynomial. So c plus bx plus ax squared plus dx cubed. Make sure it's not there. There you go. Plus dx cubed. So let's see what happens if I plot this. This is looking a little bit more interesting. Okay, so let's see what happens if I change the d. Okay, so I'm basically getting a bit of a squiggly graph. It looks a bit like the Loch Ness Monster, right? You can basically change the graph properties like this. So these are all cubic graphs, right? So basically the cubic graph is a little bit more interesting with how it works. Okay, and again, changing the c will move this graph up and down. Okay, so these are the four polynomials that I've shown you. And of course, there are an infinite number of polynomials because I can just keep on adding extra terms with higher and higher powers. But let's just focus on the four which we looked at. So the first one was the constant polynomial. That was just simply how high or low the graph was. So that was just simply a horizontal flat line. All right. Then we looked at a linear polynomial. So this was a little bit more a linear straight line, right? Then we looked at the quadratic polynomial. So this is our U shape, and the name which we give to this U shape is a parabola. And then we looked at the cubic polynomial. So the cubic polynomial was a bit more of this kind of wavy graph that's going on. Okay, so let's actually come back and let's explore this in a little bit more detail and make sure we've got this. So one way that we can describe what's happening with these polynomials is the shape, just simply seeing what's happening with the different shapes of the polynomials, and that's important. But another way that we can describe these polynomials is using these things called roots. Now, the root of a polynomial, okay, just think about what roots means in every single day life, okay? So in English, a root is a starting point. So I've drawn a picture of a tree there, okay? So with a tree, the roots are the starting point. So with a plant, the roots are the starting point of that plant. Then everything else grows from those roots, okay? So it's the same kind of principle here with polynomials. So roots are the starting point, okay? So therefore, with a polynomial, x should be the starting point. So we've just seen some different shapes of the polynomials. So we've just understood that a polynomial also works with functions. The idea is you give me an input and I will tell you what the corresponding output is going to be. Okay, so with a polynomial, x is the starting point. In other words, we want to find the value of x. All right, so the root of a polynomial is simply a value of x, but it's a really important thing. Okay, a root of a polynomial is the value of x which crosses the x-axis. Okay, so with a function, x is the starting point. So therefore, we say a root is a point where a function crosses the x-axis. Okay, where the polynomial crosses the x-axis. So for example, if I draw a parabola, okay, which remember a parabola is the quadratic polynomial. So y equals ax squared plus bx plus c. Okay, so basically 3 terms and the highest power is 2. Okay, well, if I draw this on with some axes, all right, the roots of this particular polynomial are quite simply the values of x. They're my starting points. So what values of x am I looking at? I'm looking for the values of x which go through the x-axis. Okay, they're the values which go through the x-axis. Okay, so these here are my roots, right? The roots are the values which go through the x-axis of a polynomial. Okay, now it may be that some polynomials don't have any real roots. Okay, so what I want to do now is actually generalize this based on what we've just observed. Okay, with the different shapes of the graph. Okay, so if I come down here, so let's just remind ourselves, let's go through these one by one. Let's start off with the first polynomial that we looked at. So the first polynomial that we looked at was our constant polynomial. It wasn't the most interesting polynomial in the world. It was just simply a flat horizontal line. Okay, now just remind me, what was the degree of this particular type of polynomial? Well, just remember the degree or the order is the highest power of this polynomial. So in this case, the highest power is 0 because there's just an x to the power of 0 there. It's just we don't bother writing it. So in this case, the degree of this polynomial is 0. Now just have a think. How many roots are there? So just remember, I've just said that a root is where a polynomial, where I graph it, where does it go through the x-axis? Okay, so let's have a think. Well, if it's a constant graph, it's just a flat horizontal graph, not really doing much, and you're kind of sitting there a bit bored, right? It's never changing. It's going to be a flat horizontal line. Therefore, it's not going to go through the x-axis at all. Okay, so because it's not going to go through the x-axis at all, the number of roots are 0. Okay, let's move on to the next type of polynomial that we've got. Let's move on to this one. The next type which we looked at was the linear polynomial. Okay, well, just think, what was a linear polynomial? What was the order or the degree of the linear polynomial? Well, that was the highest power, and in this case, the highest power is 1. It's just we don't bother writing it. The highest power is 1. Okay, so therefore, because the highest power is 1, the order and the degree of that polynomial should be 1. Okay, and that was that kind of line. Okay, hence why we call it linear. So it looks a bit like a slide if you want to remember it that way. So how many roots should this polynomial have? Well, if you think, because it's a line, okay, it's basically going to keep on going up in that direction and down in that direction, but it should cross the axis. And it will cross the axis once. It will never turn round again and kind of come back and do it again, right? It's only going to go through the axis once, all right? So what was the next type of polynomial we looked at? Well, we looked at quadratics next, right? And if you remember the quadratic, the name of the quadratic was a parabola, right? The name of the quadratic was a parabola. And if you think, parabola sounds a bit like umbrella, hence the reason why I've drawn a bit of an umbrella going on there. So if you want to think a parabola is a bit like an umbrella, where it's the outside rim of that umbrella, that's fine, okay? But what's the order or the degree of that quadratic? Well, the order or the degree of the quadratic is 2. And think, if it's a line that looks like that, so it's a nice U-shaped graph, how many times should it go through the x-axis? Well, it should be twice, right? It should go through the x-axis twice. So therefore, the number of roots should be 2. And then finally, if I look at the cubic graph, so it looks a bit like the Loch Ness Monster, right? That S-shaped graph. What was the order or the degree of that quadratic? It was 3. And what was the roots? How many roots should it have? Well, if you think, because it goes up, then it goes through once, then it comes back down again, so it goes through another time, but then it comes back up again. So therefore it goes through another time. So therefore the number of roots should be 3. Now this is a really important idea, and this is the idea that I actually wanted to get across to you. The reason why I've kind of been harking on for quite a long time about polynomials, the order or the degree, and the number of roots, and particularly visualizing the shapes of graphs, the reason why I've kind of looked at that quite a lot is because the order or the degree, just remember that's the highest power, should tell you how many roots that has. Okay, that should tell you how many roots that particular type of polynomial has. And this was actually discovered. It's called the fundamental theorem of algebra. This gets so important. It's called fundamental. It was discovered by a mathematician called Carl Gauss. Okay, and it was a really important idea and central idea that the number of roots of a polynomial should be equal to the highest power. Okay, so with a cubic polynomial, there should always be 3 roots. It may be that those 3 roots are exactly the same. Okay, it may be that there's something called imaginary roots, which we don't look at in this course, but there are still 3 roots. Okay, similarly with a quadratic graph. Okay, there are always 2 roots. It may be those 2 roots are the same. It may be they're 2 different real roots, or again, it may be that they are imaginary. Okay, again, same with linear, because the order or the degree of a linear polynomial is 1, we're expecting 1 root, and the same with a constant polynomial, just y equals 3 or y equals 5 or something like that. Because the order or the degree is 0, we are expecting that the number of roots should be 0 as well. Okay. So really what we're going to look at in this course is the idea of how we can actually calculate what those roots are. Effectively, the kind of next sort of couple of weeks when we're looking at quadratics, we're effectively looking at ways of trying to understand features of those polynomials, particularly with quadratics, because the emphasis in this course is on quadratics. We're going to be looking at ways of trying to establish what those roots are. So let's actually look at an example. Okay, so we're going to look at an example of when of a quadratic polynomial. So let's suppose we look at y equals, let's say x squared plus 3x minus 4. Now, by the way, when we're writing a quadratic down, okay, in fact, when we're writing any polynomial down in general, we should always start with the highest power first. Why? Well, we've just gone through that. Because we want to establish what the highest power of that polynomial is, because then that will tell us the number of roots. It will tell us how many roots we're actually looking for, okay? So as a general rule of thumb, okay, always write the highest power first, and then the next highest power, and then the next highest power, and the next highest power. So you can see here with y equals x squared plus 3x minus 4, you can see I've written the powers in descending order, okay? Now have a look. Before I go any further, could you tell me what the coefficient, remember the coefficient is the number which multiplies the x, or the power of x at least. Could you tell me what the coefficient of this x squared is? So have a look at it. What is the coefficient of my x squared? Well, hopefully you're looking at that and going, I know, it's just 1. Because 1 times anything is just itself. So there is a coefficient there, just because we don't write it, just be aware, there is a coefficient there, it's 1. Okay, so it's 1. Okay, fine. So let's suppose I want to find the roots. So I want to find the roots of this particular quadratic polynomial. Y equals x squared plus 3x minus 4. Okay, so I want to find the roots. So just remember, the roots are the points which go through the x-axis. Okay, so the values of x for this polynomial which go through the x-axis. Okay, so if I'm going to draw this out, well, I know that this is effectively a U-shaped graph. Okay, it's a parabola. All right, and I know it's going to go through the x-axis somewhere. So I'm not going to actually draw the y-axis in because I don't know where it is yet, but I'm just going to draw the x-axis in. So the points which I'm after is this value of x here and this value of x over here. Okay, well, in order to find the value of x, I'm looking for the point which goes through the x-axis. So if I want to find the points which go through the x-axis, well, the x-axis I know is the constant graph y equals 0. Because if you think, every single point along that line is always 0. Okay, so it's y equals 0. So I'm looking for the points on this polynomial where y is equal to 0. So all I need to do is take this polynomial and say, when is y 0? In other words, I need to change the y, which is currently written there, into a 0, okay? So to find the roots, and this is really important, to find the roots, and this is true of any polynomial, okay, I need to always set y equal to 0. Okay, I need to set y equal to 0, right? So I need to find the roots, I need to set y to be 0. All right, so let's do this then. So I take my quadratic, which is y equals x squared plus 3x minus 4. And I need to change y to be 0 in order to find the roots. So I'm going to put 0 here. Can you see that? All I've literally done there is change that y into a 0, okay? All right, fine. Now, just a general rule of thumb, I'm going to write the 0 over on the right-hand side. I think it just looks a bit nicer. I tend to have the things which I don't know on the left-hand side and the things which I do know on the right. Well, I don't know the value of x in this case, so I'm going to keep those together on the left-hand side. So x squared plus 3x minus 4 equals 0. Now, my next question is, what I want to do is solve this. Remember that solve just means find the value of x. So how do I solve this particular situation here? Well, okay, I need to find the value of x, which makes x squared plus 3x minus 4 become 0. So I could just try sticking in some random values. But hang on a minute. We have already looked at algebra, right? We've already looked at this kind of idea of how do we, of sort of little techniques to be able to find the value of x. So you might, for example, start looking at an equation like this and thinking, all I need to do is add 4 to both sides, right? So I could try x squared plus 3x equals 4, if I add 4 to both sides, and then maybe I could try dividing by 3, maybe, because I see that 3 there. So let's try divided by 3. Well, x squared, got to divide that by 3, 3x, got to divide that by 3, that makes x, and then I get 4/3 over here. Okay, fine. Not looking that great. Remember that I want x on its own. Well, I could try taking away the x squared. So we try x equals 4/3 minus x squared over 3. Hang on a minute, this doesn't look quite right, does it? This doesn't look any easier than what we had when we started. So my point is, if I gave you something like this, if I gave you something like 3x minus 4 equals 0, you could absolutely solve that. That's a linear polynomial. So I could add 4 to both sides, okay, and then I could divide by 3. So I could get x equals 4/3. But with a quadratic, it's harder to solve. And that's true in general, okay? So the higher the order or the degree of the polynomial you're trying to solve, the harder it is to try and do that, okay? So quadratics, we will develop some really good stable techniques over the next kind of couple of videos and the next kind of couple of weeks in class for how to work with quadratics. But for the moment, effectively what I want to say to you is that actually, at the moment, we don't have any techniques under our belt, okay? Now, the techniques that we're going to cover to be able to solve these quadratics, okay, there's 3 of them. So we're going to look at techniques of solving quadratics, so techniques to solve quadratics, in other words, to find the roots, to find the value of x which makes this equal to 0, okay. We've got come up with 3 techniques, okay. So the first technique that we're going to look at is something called factorizing. Okay, so we're going to start looking at factorizing. Now we have already started looking at factorizing sort of algebraic expressions. We did that in a couple of videos ago, okay? But mostly we've been dealing with factorizing linear expressions, okay? So we're now going to look at trying to factorize quadratic expressions instead, okay? The next technique that we're going to learn is something called completing the square, okay? Now it sounds quite scary, but I can promise you it's not. Okay, so completing the square, that's the next technique that we are going to focus on. The last technique is actually kind of linked in with this. So I'm going to put it as like a sub technique because it's linked in with this one here. Okay, so it's linked in with completing the square. In fact, it's literally completing the square, but in general form. It's called the quadratic formula. Okay, so the nice thing is at the end of this, we're going to derive a really lovely formula for us to be able to use and to solve every single quadratic we like. But we need to look at factorizing first, and then we need to look at completing the square before we get there, okay? But remember, the whole idea of this, okay, I can't emphasize this enough, the whole point of doing these techniques is that we are simply trying to find the roots, okay? Trying to find the roots, find the places which cross the x-axis. Reason being, because the roots are the starting point of our polynomial. So if we understand the polynomial, if we want to understand the polynomial, we need to understand the points where they go through the x-axis. So let's make a start then. Let's actually have a look at one of the techniques that we can use to solve a quadratic, okay? And it's going to be something called factorizing, okay? So factorizing, if you remember, we've already looked at this, but with linear expressions. Factorizing is the opposite of expanding, okay? So if you remember, expanding is the process of getting rid of the brackets. It's making something bigger, so it's getting rid of the brackets, okay? Factorizing is the opposite process. It's simply putting the brackets back in, okay? So as an example, let's suppose we have x plus 3 times by x plus 4, okay? So let's expand these, okay? Let's expand these. Well, if you remember the process to expand them, we simply need to make sure that everything in the first bracket meets up with everything in the second bracket. If you remember, it's like Mr. X and Mrs. 3 going to visit the other Mr. X and other Mr. 4 living in a house. So it's rude not to visit everyone. So everyone in the first bracket has to meet up with everyone in the second bracket. So the X has to meet up with the X and the 4, okay? So if you remember, X times X makes X squared. Then you have x times 4, which makes 4x, and of course it's positive, because it's positive times positive. And then finally, the 3 has to meet up with everyone as well. So we get 3 times x, which is 3x, and then 3 times 4, which is 12, okay? So then in total, we get x squared plus 3x plus 4x, well that's 7x, plus 12, once we simplify this, okay? So I want to really kind of focus on what's happening here, okay? It's really important that we understand where these numbers come from. Well, first things first, let's understand the x squared. Where has the x squared come from? Well, the x squared has come from the x times the x, okay? So the x times the x will give us the x squared. So if you see a quadratic, okay, and if you end up with an x squared, you can just think, okay, I've got two brackets and I've got that by multiplying x times x. So the x has to go at the start of both brackets, okay? Where has the 7x come from? Well, the 7x has come from, obviously there's the x in there, but it's come from these two numbers here, the 3 and the 4. So if you remember, we got the 4x and then we got the 3x and we ended up adding it together, okay? So the 7x came from the 3 plus the 4, okay? So these two numbers that sit here and here, this number and this number, gives us a 7x by adding them. Now, if you have a think, where's this 12 come from? Well, this 12 has also come from those two numbers, hasn't it? That 12 has also come from those two numbers, but it hasn't come from 3 plus 4, it's come from 3 times 4, okay? So in other words, if we want to factorize it, just remember factorizing is going back in the other direction. So if I take my x squared, maybe plus 4x plus 3, okay, if I want to factorize this, it means that I want to put the brackets back in. Well, I know because it's a quadratic that I'm expecting two sets of brackets, okay? I know that because I've got an x squared, that comes from the x times the x, okay? I established that in the last example. So really what I'm doing here is expanding takes us from here to here. Factorizing will take us back from here to here, okay? So let's think. I'm looking for a number that goes here and here. Well, I've kind of established what those two numbers have to do from my previous example, thinking about expanding, okay? The number which goes here and here, which I've shaded in red, they have to add together to make 4, okay? So they have to add together to make 4. So basically what I'm saying is that something plus something has to make 4, okay? So something plus something has to make 4. But those two numbers have also got to multiply together to make 3. So in other words, that something times the other thing has got to multiply to make 3. So let's just think, okay, I'm looking for two numbers, and the two numbers have got to do two things. They've got to add together to make 4, and they've got to multiply together to make 3, because that tells me that in my quadratic. So always start from this bottom one. Always start from what multiplies to make 3, because there's going to be fewer things that multiply to make 3 than add together to make 4. In fact, there's an infinite number of things which can add together to make 4, but there's only a finite number of integers which can multiply together to make 3. And the key is here, I'm looking for integers, right? I'm looking for whole numbers, right? So let's think, what are the two numbers that multiply together to make 3? Well, I've got 3 times 1. That definitely works. Okay, so I've got 3 and 1. I've also got negative 3 and negative 1. So remember, I've also got negative 3 and negative 1. Because negative 3 times negative 1, that also makes 3. Okay, so basically I've got two sets of numbers that could go here. Either negative 3 times negative 1 or 3 times 1. So now I need to look at which of these satisfies the first situation, which is that they've got to also add together to make 4. Well, if it's -3 and -1, we'll have a look. -3 plus -1, that makes -4, right? Which is not what I want. I don't want -4. So let's try 3 and 1. Well, 3 plus 1 also makes 4. So therefore I know that because 3 times 1 makes 3, and 3 plus 1 makes 4, therefore I know that the two numbers that go here and here are +3 and +1. Okay, so +3 and +1. So to factorize, you're just thinking, right, the two numbers that go here and here in red have got to multiply together to make that last number, and they've got to add together to make that middle number, the term in x, okay? Let me show you with another example. Let's try x squared plus 5x, let's say plus 6, okay? So therefore, I set up my two brackets the same as before, okay? I put my x at the start of both of them because I know they've got to multiply together to make x squared, okay? But then the two numbers that go here and here have got to multiply together to make 6. So I'm basically looking for something times something to make 6. And they've also got to add together to make my 5. So that's something plus something has got to make my 5. So let's have a think, okay? Let's first of all start with the multiplying to make 6 condition, because there's going to be fewer numbers there. So let's think, well, I could have obviously 6 and 1, and of course I could have -6 and -1. Okay, and I could also have, what else could I have? Well, I could also have 3 and 2, guess that would work. And of course I could also have -3 and -2 as well. All right, so let's see which of these pairings work. Well, let's just start with 1 and 6, okay? Let's start with 1 and 6. So I'm going to check this in my 5. They've got to add together to make 5. Well, does 6 plus 1 make 5? No, it doesn't. It makes 7. So I know that that one's ruled out, so I can put a big cross through that one. Let's have a look at the -6 and -1. Does -6 plus -1 add together to make 5? No, it doesn't. It adds together to make -7. So that one's also ruled out. So what else have I got? Well, 3 and 2. Does that add together to make 5? Well, 3 plus 2, yeah, that makes 5. So I think the one that works here is +3 and +2. They're both positive, okay? So in other words, I'm saying that x squared plus 5x plus 6 can add together, can factorize to x plus 3 times by x plus 2. Let's do it with another example. In fact, let's do it with the example which we originally wanted to solve. So we originally had x squared plus 3x minus 4. Okay, so we're going to try and factorize this, see if we can find the roots. Okay, so x squared plus 3x minus 4. Well, let's see. Okay, set up my two brackets first of all, stick an x at the start of both of them, and they've got to multiply together to make 6. Sorry, multiply together to make -4. Make sure you capture that negative. Don't just put 4 down, okay? It's -4, all right? And they've also got to add together to make 3, okay? They've got to add together to make 3. So let's go through this and let's see if we can think of two numbers which multiply together to make -4 and add together to make 3. All right, so here we've got a bit more careful because we need to multiply together to make a negative. So the only way that two numbers can multiply to make a negative is if one of those is negative. So we've got to have one negative, one positive. So it's just going to make our options a little bit more, we need to consider more options, but that's fine. So I'm just going to try different options here. Let's try, first of all, the obvious one, which is -4 times +1. Okay, so -4 times +1. Does that add together to make 3? No, it doesn't. It makes -3. Okay, so let's try a different option. Let's try, for example, +4 and -1. Okay, well, +4 plus -1, that makes 3. So therefore, it's got to be +4 and -1 there. Okay, so let's just try it with another example. Let's just try factorizing with another example. Let's try x squared minus 6x. Let's try x squared minus 6x minus 7. All right, let's try that. So therefore, I'm looking for two numbers. So first of all, let's set up my bracket. So bracket, 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 stick an x at the start of both. So I'm looking for a number here and a number here. Now these two numbers have got to, well, they've got to multiply together to make -7. So something times something, which multiplies together to make -7. And they've also got to add together to make my -6. So something plus something has got to make -6. Remember, keep that negative there. That's really important. Okay. So let's go through this. Multiply to make -7. Well, we've got a couple of options here. Remember, it's a multiplying to make a negative, so one of those numbers has got to be negative. We could have 7 times by -1. Okay, 7 times -1. So let's try that. Do those two numbers add together to make -6? Well, 7 plus -1, that's the same as 7 take away 1. No, that's +6. So the other option I could have is -7 times +1. So let's see, -7 plus 1, does that make -6? Yes, it does. So therefore I know the number goes there has got to be -7, and the number that goes there has got to be +1. Now it doesn't matter in which way round they go, so I could equally put it round the other way. So I could put +1 here and -7 here. It will matter with some examples we do later on, but we're not there yet, okay? So in this case, if you've just got x squared at the front, you can just basically stick those two numbers in either order. Now the big question is, how does this help us? How does this help us find the roots of our quadratic? So if you remember at the very start, we had x squared plus 3x minus 4, or y equals x squared minus 4, plus 3x minus 4, and we wanted to find the roots. So in order to find the roots, all we had to do was set this thing equal to 0. Okay, so if we set this thing equal to 0, it means we're finding the roots. The roots, remember, are the points which go through the x-axis, and to find the points which go through the x-axis, that's the line y equals 0, we set the y to be 0. Okay, so let's try and solve this then. So x squared plus 3x minus 4 equals 0, and we're trying to solve this, okay, because we're trying to find the value of x. Well, if we use a factorizing technique, I can factorize this left-hand side here. Okay, so I know we've done it before, but I will do it again just for practice, just to make sure that we're okay with this. So remember, I first of all start by setting up my two brackets. So there we go. Keep the equal 0 this time because the right-hand side isn't changing, so it still equals 0. Put the x at the start of both brackets. And then I'm looking for two numbers that multiply together to make -4. So it's always multiplied together to make that last number. And they have to add together to make the 3. Okay, the 3 here. So we've got to add together to make 3. So let's think, two numbers that multiply together to make -4, add together to make 3. The more practice you do with this, you'll be like, I can do this really quickly. But for the moment, whilst you're getting used to it, let's start off with the facts of -4. Well, I think 4 and -1 would work. So 4 times -1 would make -4, and 4 plus -1, that would make 3. Okay, so I know that it's got to be +4 here and -1 here. Again, it doesn't matter what order I put the +4 and -1. Okay, so ordinarily we'd leave it here if we were just factorizing it. But because we want to solve this, okay, in other words, we want to find the values of x, okay, because we want to solve this, what we're going to have to do is try and consider what this means. So what's basically happening here? This x plus 4, well, x is just a value, and it just basically means some value plus 4. In other words, that's just a number. X plus 4 is just a number. And likewise, x minus 1 is also just a number, okay? So x plus 4 is a number, x minus 1 is also just a number. It's just we don't know what the value of x is at this stage, okay? So the x is just a number, could be 5, could be 7, could be -2, whatever it might be, but we're going to add 4 to that number. So therefore, we're just going to get a number on the red. The second bracket is also going to be a number for the same reason. Then just think, what are we doing with those two numbers? Well, we're multiplying them. Are you happy? We're multiplying these two numbers together. And the point is, we're multiplying these two numbers together and they equal 0. So let's just do a very quick thought experiment here, okay? What we're basically saying is that we've got a number times another number and it has to equal 0. So let's suppose, for example, we might have 3. Now, what happens if I take 3 and I multiply it with 0? Well, 3 times 0 is 0, okay? Let's see if we take another number. Let's take like 0 times 5. What's 0 times 5? Well, 0 times 5, that's just 0 again. What about if we take -2 and multiply it with 0? If we take -2, multiply it with 0, that is also 0. What about if we play 0 and we try -10? Well, lo and behold, that is also 0, okay? So any number times 0 should equal 0, okay? Now that's going to help us out here, because we've basically said this is a number, the x plus 4 is a number, and we're multiplying it with another number, that's this x minus 1, that's also another number, but it equals 0. So we've just seen over here on the right hand side, if you take two numbers and you multiply them together and it equals 0, at least one of those numbers has to be 0. That's the only way you can get 0 from multiplying two numbers together. One of those numbers has to be 0. So in this case, we've kind of got free reign. It can be either one of them. It could be this one which equals 0, so x plus 4 could equal 0. Or it might be this one. Okay, so or it might be x minus 1 that equals 0. Okay, so it could be either one of those. As long as one of them equals 0, we're always going to get equal 0. In fact, it could even be both of them. It doesn't matter. So either x plus 4 equals 0 or the x minus 1 equals 0. Okay, so then from here we can actually just solve this. So if x plus 4 equals 0, then in order to solve this, we take away 4 from both sides, which leaves us with x equals negative 4. Okay, x equals negative 4. If this thing equals 0, if the x minus 1 equals 0, in order to solve this, all we've got to do is add 1 to both sides. So therefore, x equals 1. Now it's really important that you put the word or down the middle, because it could be this thing or this thing, but not both at the same time. It can't be and. So it's either x equals negative 4 or x equals negative 1. You can't be both negative 4 and 1 at the same time. Okay, you're either negative 4 or you're 1, you're not both at the same time. Now, why is that important? So basically what we've done here is we've found the roots of our quadratic, okay? So actually if I plot the x squared plus 3x minus 4, let's see what we get. So if we come back to GeoGebra, let's see what we get. So if I plot x squared plus 3x minus 4, ooh, this is interesting. So this is the quadratic. This is our parabola shape which we expect. Remember, it's that U shape, right? It's this U shape, and remember we're after the roots. We are after the points which go through the x-axis. So we're after that point there, and we're after that point there. We'll have a look. This point here is negative 4, 0. Well, isn't that what we've just found? We've just found x equals negative 4. And if you have a look, this point here is 1, 0. Well, isn't that what we've also just found? We found x equals 1. Okay, so therefore, this is literally what we wanted. These values of x literally correspond to the points which go through the x-axis. Okay, which go through the x-axis. Now I wonder if I can give you one to have a go at yourselves. Okay, so let's try solving. In fact, no, let me do it more generally. Okay, can you find the roots of this quadratic polynomial for me? Okay, so can you find the roots of y equals x squared plus 8x minus 9? Okay, can you have a go at that one for me? So can you have a go at finding the roots of y equals x squared plus 8x minus 9 for me for homework? And if you've got any problems, then please bring it along to the lessons, and I'm sure your teacher is more than happy to help.